Welcome to Etymology of Rocks, a guide to common rock and mineral terminology. This video will cover some basic terms you'll hear when talking about rocks and minerals. Let's start with part 1. What is a mineral and how do minerals form? Section 1. Types of rocks. Igneous. These rocks form from volcanic activity. There are two types of igneous rocks: intrusive, which cools below the surface of existing rock layers and forms coarse-grained rocks such as granite, and extrusive, which cools on the surface and forms fine-grained rocks such as basalt. These rocks can also be divided into felsic, containing light-colored silica-rich minerals, mafic, containing darker iron and magnesium-rich minerals, intermediate, in between felsic and mafic, and ultramafic, mostly containing mafic minerals. So here we have granite as an example of an intrusive rock, and then basalt as an example of an extrusive one. Now, as you can see with the basalt, there's little white bits, those are zeolites, but the black part is the basalt. And here we have quartz representing felsic minerals, plagioclase feldspar representing mafic, diorite representing intermediate, and peridot representing ultramafic. And just to be clear, the peridot's the green part, there's also basalt around that. Sedimentary. These rocks form from the compaction of sediment, which is called lithification. There are three types of sedimentary rocks: clastic, chemical, and organic. Clastic sedimentary rocks such as sandstone or conglomerates form from the cementing of particles of other rocks or just other rocks. Chemical sedimentary rocks such as halite form as deposits of sediment that was once dissolved in water. Organic sedimentary rocks such as coal form from the compaction of decayed plant or animal material. So here we have sandstone and conglomerates representing clastic sedimentary rocks, halite representing chemical sedimentary rocks, and anthracite coal representing organic sedimentary rocks. An interesting thing about anthracite coal, there's different types of coal, so there's also bituminous and lignite, both of which are a bit less compacted than anthracite, which makes them a bit less stable. Anthracite coal is more stable and it burns longer because of the fact that it's been compacting for longer. It's from a deeper layer. Metamorphic. These rocks form when existing rocks are altered by heat, pressure, or chemical reactions. These rocks often end up with different textures and patterns, including foliation, which is a layered or banded appearance that can be seen in minerals such as gneiss. Here's a rather nice gneiss with banding that's caused by temperature and pressure. Section 2. Minerals versus rocks versus mineraloids. A mineral is one specific thing with its own chemical composition, crystal structure, and other characteristics. A rock is made up of multiple minerals, and because of this, it doesn't have a specific chemical formula, consistent hardness, or single crystal structure. A mineraloid is a naturally occurring substance that may be hard like a rock or mineral, but lacks either a specific chemical composition or crystal structure, or is formed from organic material. On the left, we have amazonite as an example of a mineral, so those are just amazonite. Then in the middle, that's a rock, so we have peridot, quartz, epidote, and chalcopyrite all on the same rock. And then on the right, we have amber, which is a tree resin, not an actual rock. That's a mineraloid. Section 3. Mineral classes. Minerals can be classified based on their chemical compositions. There are 8 major classifications: silicates, sulfides, carbonates, oxides, halides, sulfates, phosphates, and native elements. There are also minor classifications such as arsenates, vanadates, and molybdates. So here we have quartz, which is a silicate, galena, which is a sulfide, smithsonite, which is a carbonate, hematite, which is an oxide, fluorite, which is a halide, barite, which is a sulfate, apatite, which is a phosphate, and copper, which is a native element. Then we've got adamite, which is an arsenate, vanadinite, which is a vanadate, and ilmenite, which is a molybdate. Section 4. Pegmatites, Phenocrysts, Matrix rocks, and associated minerals. Pegmatites are large igneous rocks that often contain a variety of crystals, including gemstones like beryls or tourmalines, or rare earth minerals. This is a type of pegmatite that has pink tourmaline in it. Phenocrysts are noticeable crystals that can be found within finer-grained igneous rocks, creating a porphyritic texture of uneven sizes. An example of this is the blue quartz that can be found as phenocrysts in launite, which is a type of rhyolite. Here's some launite with some nice blue quartz phenocrysts. Gotta love the fact that you can just find this on the side of a highway. A matrix rock is a rock or mineral that another mineral has grown on or in. Some are common for certain minerals and can be used to determine a mineral or where it's from, such as mica schist, which can often contain garnets. Here's some almandine garnets in mica schist. Associated minerals are minerals that are often found with each other or nearby. These combinations can vary depending on the location. For example, fluorite from the Oranga region of Namibia is often found with muscovite and schorl, but fluorite from the Cave-in Rock district of Illinois is commonly found with calcite, pyrite, and other minerals. Some combinations are universally common due to chemical compositions or conditions needed to form, such as tetrahedrite with pyrite. So here we have some fluorite from the Oranga region, and as you can see, we've got some black tourmaline, which is schorl, and some muscovite. And then we've also got one from the Cave-in Rock district, and you've got some fluorite, some calcite, and some pyrite, all on one rock. And here we have some tetrahedrite with pyrite, both of which are sulfides, which commonly form with each other. And now on to part 2, crystals. Section 1, crystal systems and habits. Crystal systems are groupings of crystal shapes based on axes of symmetry and crystal lattice structures. There are 7 crystal systems: cubic or isometric, tetragonal, hexagonal, orthorhombic, monoclinic, rhombohedral, and triclinic. Each system also includes various forms. For example, octahedrons are a form included in the cubic system. These forms can be determined if a crystal has full, unbroken terminations, which can be points or flat crystal faces. So here we have pyrite, which is in the cubic system, Vesuvianite, which is in the tetragonal system, beryl, emerald in this case, which is in the hexagonal system, aragonite, which is in the orthorhombic system, gypsum, which is in the monoclinic system, calcite, which is in the rhombohedral system, and astrophyllite, which is in the triclinic system. So here we have a spinel, which has an octahedral crystal shape, which puts it in the cubic system. And then on the right, we have a quartz crystal, which has a point with faces. Now, crystal faces are also interesting because you can tell sometimes if it's natural or if it's been polished that way by looking for striations. If it's perfectly smooth with no striations, it might have been polished that way, but if it has some striations from forming naturally, well, it formed naturally. Crystal habits describe the shape or appearance of crystals, not the specific structure. There's not a fixed number of crystal habits, but some common ones include fibrous, acicular, tabular, botryoidal, dendritic, cubic, bladed, foliated, and prismatic. For number 1, we have tiger's eye, which has a fibrous crystal habit. So as you can see, it's like it's got little hairs. For number 2, we have conochalcite with an acicular or needle-like crystal habit. So it's got little puffball needles. For number 3, we have some tabular wolfenite crystals. So basically, they're flattened or kind of book-shaped. For number 4, we have some grape agate, which is botryoidal, meaning it's like little balls or like a cluster of grapes. And then for number 5, we have some dendritic agate or opal. And dendritic basically means it's branch-like. It's like a tree. For number 6, we have some cubic fluorite. So similarly to the cubic crystal system, it has cubes. For number 7, we have some bladed kyanite. So it's got those little kind of blade-like layers, right? And then for number 8, we have lepidolite, which you would have been able to see it better if I turned it on its side, but it's a little bit harder to get a good picture that way. But basically, it's layered because it's a mica. And then for number 9, we have a prismatic black tourmaline or schorl. So it's got that nice, prism crystal shape. Section 2. Microcrystalline, Cryptocrystalline, Amorphous, and Massive. Microcrystalline minerals have crystals that are too small to see with the naked eye and require a microscope to see individually. This is some green aventurine, which is microcrystalline quartz with some fuchsite in it. So technically it's a rock, but the point still stands. Now this is a microscope picture, but I've got it on my further away lens, so it's not quite zoomed in enough to see individual crystals, but they're there. Cryptocrystalline minerals have crystals, but they're too small to see even with a microscope. This is chrysoprase, which is a type of green agate. So as you can see, it's got that kind of smooth texture, but it's not totally smooth. It's kind of like fudge if you didn't melt your sugar all the way, so it's a little grainy. Amorphous materials have no defined crystals and are generally not considered true minerals due to this. However, some minerals, such as chrysocolla, which is a valid mineral species, can occur in an amorphous form. Here we've got an Ethiopian opal, which is amorphous and is considered a mineraloid. And then we've also got a chrysocolla, and this one's interesting because this one is amorphous. As you can see, it's got that kind of gelatin-like thing going on, especially up on that top layer. So it doesn't have a defined crystal structure, but some chrysocolla does. So it has both. Massive means a specimen doesn't have defined crystals due to being a broken, irregular chunk of intergrown crystals. However, they do still have a crystal structure, just not a visible one. Here's a chunk of massive calcite which doesn't have terminated crystals, it's just a chunk. Section 3. Polymorphs, Pseudomorphs, Secondary Minerals, Isostructural minerals, and textural equivalents. Polymorphs are minerals with the same chemical formula but different internal structures that cause different crystal structures, hardness, tenacity, and other characteristics. Dimorphs are a type of polymorph with at least 2 mineral varieties, such as calcite and aragonite. So these are kyanite, selimonite, and chiastolite, which is a type of andalusite, and they're all polymorphs. They all look very, very different, but they all have the same chemical formula. Then, of course, we've got some calcite and aragonite, which, again, are dimorphs, and these two don't really look very different, but calcite and aragonite can look very different. Pseudomorphs occur when one mineral is replaced by another while keeping the original shape. There are 4 types: alteration pseudomorphs, incrustation pseudomorphs, infiltration or substitution pseudomorphs, and paramorphs. Alteration pseudomorphs such as limonite after pyrite occur when the chemical composition or internal structure changes. Incrustation pseudomorphs such as linerite on galena occur when one mineral grows as a coating over an existing mineral. Infiltration pseudomorphs such as petrified wood occur when a new mineral grows into space left by a different mineral's crystal or a piece of organic matter that has since dissolved or eroded away. Paramorphs, such as brookite after rutile, occur when the internal crystal structure changes to a more stable form. So here's some limonite after pyrite, which is an alteration pseudomorph. Then we've got actually a double incrustation pseudomorph. So we have a top layer of druzy quartz that's formed over linerite that's formed over galena. And then we've also got an infiltration pseudomorph in petrified wood, which it's actually got some tiny little quartz crystals in there that have filled in cracks in the wood as that silica-rich solution has filled in that wood. And then we've got a paramorph, so brookite after rutile. So this was a rutile crystal, but it changed into brookite over time to become more stable. Secondary minerals can be pseudomorphs, but not all are. They can occur when a mineral oxidizes or is otherwise altered in a way that changes the chemical composition, or they can form as new minerals after existing ones have broken down and left behind the elements needed to form something new. So these are malachite, azurite, and turquoise, all of which are secondary copper minerals. And malachite and azurite are also common pseudomorphs of each other and of other things. Isostructural minerals share the same crystal structure with an identical or nearly identical atomic arrangement. For example, calcite and rhodochrosite are both carbonate minerals with one key difference being the inclusion of calcium versus manganese in the chemical formula and crystal lattice. Here's some calcite and some rhodochrosite. They're very similar minerals, so obviously we've got calcite, which is a calcium carbonate, and then rhodochrosite, which is a manganese carbonate. But they also have very similar crystal structures, and sometimes paler rhodochrosite or, pink calcite that can have manganese can look really similar to each other. Some rocks are textural equivalents, meaning they're comprised of the same things, but they formed at different levels and cooled at different temperatures, which caused different rates of cooling and different crystal sizes. Granite and rhyolite are examples of this, with granite being a phaneritic, meaning large-grained, version of the aphanitic, meaning fine-grained, rhyolite. Here's some granite and some rhyolite. And as you can see, the granite has large crystals, whereas the rhyolite has tiny ones. And the reason why is because the granite got to cool for longer and grow bigger crystals because it was at a higher sustained temperature. It didn't cool really quickly and only get to form tiny crystals. Section 4, Twinning. Twinning refers to crystals that have grown together in different directions, but sharing the same lattice points. There are three main types: contact twins, which join at a single plane, penetration twins, which appear to have grown through each other, and polysynthetic twins, which include parallel or nearly parallel crystals. Within these types, there are twin laws, which define the orientation of twinned crystals based on symmetry. Here we have a twinned actinolite, which is a penetration twin, and an iron cross twin law pyrite, which is another type of penetration twin, but again, it's iron cross twin law, which is specifically a pyrite twin law. Section 5. Inclusions, Law of Superposition, Phantoms, Impurities, and Color Zoning. Inclusions refer to bits or whole crystals contained within another mineral. Sometimes these inclusions cause stunning optical effects, such as the hematite flakes in sunstone, or change the color of a rock, such as fuchsite in aventurine. So here we have chlorite quartz, which is quartz with chlorite inclusions. So those green bits up at the top are caused by chlorite within the quartz. And then we've got an Oregon sunstone, which is similar to a regular sunstone, except instead of hematite, it's got copper flakes in it. It's kind of like glitter. And then we've got a green aventurine, which, like I said before, the green color is caused by fuchsite. The law of superposition is the principle that in undisturbed sedimentary rocks, the layers at the bottom are the oldest. It also applies to some rocks where one crystal or group of crystals has grown around an existing one, designating the internal structure as older than the external one. So here we have a banded carnelian. So basically those bottom bands are older layers than the top bands. And then we have a garnet within a garnet. So hypothetically, according to the law of superposition, that internal garnet is older than the surrounding garnet. However, that doesn't apply to all inclusions because, as we talked about earlier, some minerals are intrusive, which means they can grow within an existing mineral. So if it's intrusive, it's probably younger than whatever it grew into. But if it grew around something, then whatever it grew around is older. Phantoms are caused by a crystal that's had another crystal grow over it, but the original is still visible within. This is a fluorite with phantom crystals. So those purple cubes on the inside are the phantoms, and the white fluorite grew over it. Now, these phantoms aren't going to sing music of the night to you, but they're still pretty cool. Impurities are minute and inconsistent amounts of elements that are enough to change the color, cause or inhibit fluorescence, or give a mineral trace radioactivity, but not enough to truly change the chemical formula. So here we have sapphire and rubies. Now, both are corundum, so they're the same mineral, but the sapphire gets that blue color from iron and titanium, but ruby gets its red color from chromium, and that chromium also causes it to be fluorescent. This is a zircon, which is kind of a little bit radioactive, but just trace radioactivity because it has uranium within its crystal lattice, and that also makes it fluorescent. Color zoning is caused by different elements present during the formation of a crystal and can appear as bands or layers of different colored material within one crystal. This is a rainbow fluorite, which has bands of different colors. So these colors were caused by different elements being present as each layer formed. Section 6. Mineral groups, series, and analogues. Some minerals, such as garnet or tourmaline, have many varieties caused by elemental impurities, so they have groups to include each variety. Some mineral groups, like the spinel group, however, contain isostructural minerals, and their similarities cause them to be grouped together despite having different chemical formulas and sometimes different crystal structures. In the first picture, we have different types of tourmaline. So number 1 is elbaite, number 2 is dravite, 3 is lidicotite, 4 is indicolite, 5 is another elbaite, 6 is schorl, 7 is verdolite, and 8 is rubellite, all of which have different colors based on different elemental impurities, but are all still tourmaline. And then the second picture, we have different spinel group minerals. So number 9 is a regular spinel, number 10 is a haussmannite, and number 11 has a lot of things, but the black bits are franklinite, which is in the spinel group. A series consists of at least 2 minerals with the same structure, but a variation in their compositions. Some have intermediate members that represent a shift from one end member to another. So here we have some minerals in the vanadinite series. So vanadinite on the far left can form a series with pyromorphite, which is in the top right corner, and the vanadinite has, vanadium in it, and then the pyromorphite, where vanadinite has vanadium, the pyromorphite has phosphorus. And then in the bottom right corner, we have mimetite, which has arsenic in that spot. And that intermediate member there is endlichite, or arsenic-bearing vanadinite, which has a bit of both and is therefore intermediate. Some minerals have analogues, which are similar minerals with different elements or ions occupying the same space in their crystal lattices. These are cotagite and erythrite. So cotagite is the zinc analog of erythrite, which has cobalt in the place that cotagite has zinc. Part 3. Physical properties. Section 1. Hardness, tenacity, streak, and effervescence. Hardness is a diagnostic property measured by how hard an object must be to scratch a mineral, and is quantified using the Mohs scale. This is a picture of the Mohs hardness scale, which has reference minerals, so those are at even numbers, and then some common objects that can be used to test hardness if you don't have an actual hardness testing kit. Tenacity refers to how easily a mineral breaks, bends, or deforms under stress. This picture shows a collection of minerals with different tenacities. So you have some that are brittle, so they break pretty easily. You have some that are kind of flexible, so they can bend pretty well. And then you've got some that are malleable, which means, they can be warped into different shapes without breaking. Streak is another diagnostic property that refers to the color left behind when a mineral is scratched across a ceramic streak plate. This is a chart of different minerals that have different colored streaks. So if you know the streak color a mineral leaves behind, if you test it and it leaves that color streak, it can kind of narrow down some of the things it could be. Effervescence is a release of gas bubbles that appears as fizzing when a mineral reacts with acid. It's commonly used to identify carbonate minerals. This picture shows the chemical reaction when you expose a carbonate, in this case calcite, to acid, in this case hydrochloric acid. Section 2. Fracture and cleavage. A mineral's fracture is the shape left when it breaks. For example, quartz has a conchoidal fracture, and limestone has an uneven fracture. So on the left, we have an obsidian with a nice defined conchoidal fracture. And as you can see, it's kind of like a scallop shell, which is why it's called conchoidal, like a conch shell. And then on the right, we have a septarian, but it's mostly the limestone that's broken, and that has an uneven fracture. So it just broke apart without really leaving a defined shape. Cleavage refers to how a mineral breaks along specific planes. Different types of cleavage are decided by how many cleavage planes there are, where they are, and how clean the broken surfaces are. This chart shows the number of cleavage directions, the shape, some pictures of the rocks, and the directions of the cleavage planes. Cleavage planes are also kind of important because sometimes they can cause some minerals to break really easily. Like, for example, topaz is kind of rare to find on its matrix because it has perfect basal cleavage. So at the bottom of the prism, it breaks really easily. So it commonly breaks off of its matrix, and you get loose crystals. Section 3. Density and specific gravity. Density is measured by dividing a mineral's mass by its volume and can be used to determine what a mineral is. Here we have a white opal and some gold. So the opal has a density of 1.9 to 2.3 grams per cubic centimeter, and the gold has a density of 19.32 grams per cubic centimeter. So the gold is a lot denser than the opal. Now, this can be important because while you wouldn't really confuse opal and gold, there's other minerals that are easily confused, like blue topaz versus aquamarine, which I've had happen before personally because my box got mixed up and things ended up in the wrong spaces. So, gotta figure out which is which, and blue topaz is denser than aquamarine. So it can help to know the density so that way you can figure out what's what. Specific gravity involves weighing a mineral by itself and in water, then using an equation to calculate the specific gravity using those weights. This picture shows the different methods of weighing your specimen and the equation you'll need to get the specific gravity. Part 4. Optical Properties. Section 1. Luster and Refractive Index. Luster refers to the way light reflects off the surface of a mineral. It's divided into two main categories, metallic and non-metallic, which includes vitreous or glassy, pearly, silky, resinous, greasy, earthy or dull, and adamantine. Now, I've already done a luster video. I'm not going into the full thing for luster for this too. I'm going to link my previous luster video. I'm going to try and have it be that little clickable link up in the top corner, but if that doesn't work, it'll be in the description. A mineral's refractive index is a measure of how much the mineral bends light that passes through it. It's an important diagnostic measurement that can help to identify a mineral as well as tell if it's genuine, synthetic, or fake altogether. So this is a blue topaz, and on the right, that's a picture of my refractometer measuring that blue topaz. So its refractive index is approximately 1.61, which puts it within range of blue topaz. So that tells me that that's blue topaz. That's not aquamarine, that's not blue zircon, it's blue topaz. Section 2. Dispersion, Birefringence, Pleochroism, and the Alexandrite effect. Dispersion refers to how white light separates into its component colors when it passes through a mineral, which is what causes a play of color or fire in gems such as diamond or moissanite. This is a synthetic moissanite, so those little sparkly, colorful bits in it are caused by dispersion. Birefringence, which is also known as double refraction, is where light is split into two rays that bend at different angles upon exiting a crystal, which causes objects seen through the crystal to appear doubled. So this is a calcite crystal, and calcite crystals like this are called optical calcite because they have that double refraction. So as you can see, the paper behind it, I wrote double refraction, and you see two of those. So double refraction can also be checked using a tool called a dichroscope, and that can be used for diagnostics. So for example, the other day I was looking at a benitoite. Well, I was looking at a blue faceted gem that I thought was a benitoite, and I was checking to see if it had double refraction, because if it did, then it was probably a benitoite. And so again, I used my dichroscope for that. Unfortunately, I couldn't get a picture of that though, because it would be like trying to get a picture through a pen light, so that wouldn't really work very well. This is easier to actually see it. Pleochroism is an optical effect where a mineral appears to be different colors when viewed at different angles. It's due to the mineral's crystal structure absorbing light in different amounts depending on the direction. For example, we have a Vivianite, and yes, I know, not a Tanzanite, the quintessential pleochroic mineral, but anyway, as you can see, in the red circled portions, on the left, it's green at that angle, but turned very slightly, that green area becomes blue due to the Pleochroism. The Alexandrite effect is a color change in different kinds of light, which is caused by how impurities interact with light and different wavelengths present in natural, incandescent, and fluorescent light. So, quick disclaimer on these. This is a synthetic Alexandrite, first of all, and second of all, my phone wasn't quite picking up some of the blue colors. It was only really picking up purple for some reason, but in person you do see more of the blue. But anyway, so in the first picture, that is natural light indoors. The second picture is natural light outside. The third is an LED light. And then the fourth is incandescent. Section 3. Chatoyancy and Asterism. Chatoyancy, or the cat's eye effect, is common in fibrous minerals and is caused by light reflecting off of individual fibers. This is petersite, which is formed from chrysotolite that has become silicified. So those little fibers in there give it that reflection that's chatoyancy. Asterism is caused by thin fibers of rutile or occasionally hematite in a mineral reflecting and scattering light to create a star-like pattern across the piece. The fibers must be aligned just right to create a full star, and usually polishing is required to truly reveal it. This is a star ruby, which has little inclusions of rutile that give it that star. Fun thing about star rubies and other gems, you can tell sometimes if one's synthetic if the star is always visible in any lighting at any angle. If it's like that, it's synthetic. But if the star only appears at certain angles with light on it, then it's probably real. Section 4. Fluorescence, Phosphorescence, and Tenebrescence. Fluorescence occurs when a mineral with specific ions or impurities is exposed to ultraviolet light at a certain wavelength that activates them. Some elements, such as chromium, commonly cause fluorescence, while others, like copper, commonly inhibit it. Different wavelengths of UV light also produce different results. Some minerals only react to shortwave, midwave, or longwave, while others may react to more than one and may present different colors depending on which is used. So we've got ruby, which again has chromium that causes fluorescence. And then on the right, we have orichalcite, which is a copper mineral, and it's not fluorescent. It kind of just reflects the UV light a bit. And there might be a couple things on it that are fluorescing, but it's just dust. Here we have trilingua-calcite, which fluoresces under shortwave and longwave, and then euperlite, which only fluoresces under longwave. Phosphorescence occurs after fluorescence when excited electrons are temporarily trapped in a higher energy state and require time to release it after the UV light is removed. Here's a very phosphorescent willemite. And it's still going. Tenebrescence is a temporary movement of electrons in a crystal lattice following UV exposure, which causes minerals to appear a different color for a short time. Here we have Hakmonite, which on the left is, in its regular state, and then did some UV light, and then on the right, you see that color change, especially in that one on the left, where it was mostly kind of white before. Now you can really see the purple, and the other one is darker. Section 5. The Schiller effect, or Labradorescence, Aventurescence, and Adulorescence. The Schiller effect is a colorful flash caused by light hitting lamellae, which are small parallel particles within a mineral. It's primarily seen in labradorite, which is why it's also known as Labradorescence. So here's some labradorite, and you can see that nice colorful green flash. And then on the right, that's the microscopic picture. So all of those little fibers, those are the lamellae, which are what causes it. And that's one of my favorite things to look at under the microscope, just because that's not something that you normally see. So it's kind of cool getting to actually see that bit. Aventurescence is a similar effect caused by inclusions such as hematite or copper, and it can be seen in sunstone. So here's some sunstone, and this one really looks like glitter. The only thing cooler than this, in my opinion, is iolite sunstone, which is iolite that has little hematite bits in it as well, so it looks like sunstone, but it seriously just looks like glitter, and it's awesome. Asterism is caused by particles of adularia and can be seen in moonstone. This is rainbow moonstone, and that flash is the asterism. Section 6. Triboluminescence, pyroelectricity, and piezoelectricity. Triboluminescence is light produced by mechanical actions such as pressure or friction. Quartz crystals can exhibit triboluminescence when rubbed against each other or broken. This picture shows quartz crystals being rubbed together, which is producing light because of triboluminescence. Could this be used to, signal people if you're lost in the woods? Maybe. Depends on how dark it is, but either way, it's pretty cool. Pyroelectricity is the ability of a mineral or other substance to generate an electric charge when heated. This is dioptase, which is pyroelectric. So if it's heated, it can generate an electric charge. Piezoelectricity is similar to pyroelectricity, except it requires the application of pressure, not heat. This is a quartz crystal, and quartz is piezoelectric. And fun fact about this, quartz actually used to be used in clocks and watches because it's piezoelectric. Part 5. Lapidary and jeweler terms. Section 1. Lapidary and cabochons. Lapidary is the art of shaping stones, including polishing, cutting, carving, engraving, and faceting. These are some various shaped stones. So number 1 is a cut stone, it's a turquoise. Number 2 is a faceted spinel. Number 3 is an opal cabochon. And number 4 is a polished nunderite. Cabochons are cut and polished rocks that have a flat side and a domed side, and have been cut into a certain shape. These are labradorite cabochons. So on the left, you can see the domed side, and the one actually has some facets, whereas the other is just rounded and smooth. And then in the picture on the right, that's the backside, which is flat. These are commonly set into jewelry backings, so like for necklaces, for example, which is why you'd want a flat side. Section 2. Facet patterns and the 4 C's of diamonds. Facet patterns are the specific arrangements and shapes of flat surfaces, or facets, cut into gems. There are many different patterns to create the ideal gem with maximum brilliance, depth of color, and other desirable qualities. Here we have a variety of faceted gems, all of which are different shapes. Certain gems are usually cut into certain shapes. So, like emerald, for example, has a specific emerald cut, whereas other gems might have their own cuts based on what highlights important things about that gem. The 4 C's of diamonds are cut, clarity, color, and carat, all of which are used for grading quality. These refer to the shape and brilliance, transparency without inclusions or internal fractures, color and vividness, and weight of the diamond. However, similar criteria are used to grade other faceted gems such as rubies, sapphires, emeralds, and topaz, and the parameters for quality vary depending on the standard for each. This chart shows the 4 C's and how they work. Now, again, for other gems, it can vary a little bit. Like, for example, with emeralds, the clarity isn't really the same as for a diamond, because for a diamond, they're supposed to be totally clear. But emeralds very rarely actually come like that, so a few inclusions or a few tiny fractures can be negligible. And for some gems, brilliance also isn't really as important because they have a lower refractive index and therefore they don't have the same brilliance that a diamond would. So holding them to the same standard doesn't really work. They'd all be low quality by that metric. Section 3. Synthetics, Heat Treatment, and Trade Names. Many popular gems have synthetic counterparts. These are often cheaper alternatives for rare gems, but they can also allow for easier faceting with less waste due to their lack of inclusions and fractures and even color. However, they can sometimes be confused for natural gems if not properly labeled. Here we have a synthetic Alexandrite, a synthetic blue zircon, a synthetic moissanite, and a synthetic sapphire. Natural Alexandrite, blue zircon, and moissanite in particular are pretty rare, especially considering some of them only come from certain places, which can make them hard to obtain. Synthetics can be, again, a cheaper option, but there's a bit of an issue sometimes when they're not labeled properly or people try to sell them as natural gems. And that's part of why gemologists are important, because they take classes and use tools that can basically prove that a mineral or a specimen is real versus synthetic. So if you're not sure if something's real or not, you can take it to a gemologist and have it checked, and if you think it is real and you want to get it certified, that's an option too. Heat treatment is commonly used to enhance or change the color of a gemstone. For example, London blue topaz is often heated to produce a more vivid blue color, and most citrine on the gem market is actually amethyst that's been heated until it changed color, mimicking the natural process that creates citrine. So here's some London blue topaz, which is, again, heat-treated blue topaz, and generally it's created using some colorless to really pale blue topaz that wouldn't really be very valuable in that state. It's heated then to make it that vivid blue color, which makes it more valuable. Then on the right, we've got heat-treated citrine, which again is amethyst that's been artificially heated. So natural citrine gets that color. It starts out as amethyst, but then it gets that color over a long period of time because of the heat within the earth. And it generally gets that nice golden yellow color, whereas heat-treated citrine kind of looks like you left your bread in the oven for a little bit too long. It looks a little bit burnt. But it's a good way of being able to tell if it's natural or not. Trade names are unofficial names used by retailers to refer to a mineral in order to gain more interest and appeal. For example, cactus quartz or spirit quartz are common trade names that refer to a type of quartz or amethyst with smaller crystals grown over it. Here's some cactus or spirit quartz, whichever you prefer. Personally, I prefer cactus because it is pretty spiky. Trade names can also get a little bit funky though. For example, you've got things like Miriam stone or script jasper, which is actually a type of marine limestone with fossils that cause that pattern. It's not a jasper. So it's important to keep your trade name straight to make sure that you know what something actually is, because sometimes they're really not accurate. And that's the case for a lot of jaspers, actually. People call a lot of things jaspers that aren't jaspers. Part 6. Other terms. Type locality. A mineral's type locality is where it was originally discovered. Some minerals that have been known since antiquity don't have known type localities since their initial discovery was not recorded. This is purple aragonite, which comes from aragonite's type locality, which is the Gayo River in Molina de Aragon, Spain. Precious versus common opal. Precious opal has play of color due to dispersion. Common opal does not, though it's still opal. Here we have an Ethiopian opal, which is a precious opal, and a pink opal, which is a common opal. And as you can see, that common opal doesn't have that colorful rainbow flash, which, by the way, is also called opalescence. So that's how you can tell it's a common opal, but it's still opal, it's not agate or any of that. Tektites and fulgurites. Tektites are rocks formed by meteor impacts, melting sand or other rock, and then cooling into masses such as moldavite. Fulgurites are rocks formed by lightning striking sand, melting it, and then cooling into masses such as Libyan glass. So here we have a moldavite, which is a tektite, and Libyan glass, which is a fulgurite. As you can see, they both have that kind of glassy thing going on, and it's because they're both formed from silica-rich material melting and then cooling again, so it's kind of similar to obsidian, how that's a volcanic glass. These are basically like that, but they're not formed from volcanic activity, they're formed from meteors and lightning. So, pretty darn cool. Rare earth minerals. Rare earth minerals are minerals containing the 15 lanthanide elements as well as scandium and yttrium. These minerals are important sources of these elements, which are used in a range of modern technologies. These elements are difficult to obtain due to relatively small and scattered deposits of their host minerals and the complex methods needed to extract and refine them. These are monazite and bastnasite, both of which contain a variety of rare earth elements and are important sources of them. They're pretty rare minerals, though. And we've finally made it to the end of this very, very long video. So, thanks for watching.